In mathematics, the associative property is a property of some binary operations. In propositional logic, associativity is a valid rule of replacement for expressions in logical proofs. Within an expression containing two or more occurrences in a row of the same associative operator, the order in which the operations are performed does not matter as long as the sequence of the operands is not changed. That is, rearranging the parentheses in such an expression will not change its value. Consider the following equations. Even though the parentheses were rearranged, the values of the expressions were not altered. Since this holds true when performing addition and multiplication on any real numbers, it can be said that addition and multiplication of real numbers are associative operations. Associativity is not to be confused with commutativity, which addresses whether A times B equals B times A. However, many important and interesting operations are non-associative. Some examples include subtraction, exponentiation and the vector cross product. In contrast to the theoretical counterpart, the addition of floating-point numbers in computer science is not associative, and is an important source of rounding error. Definition. Formally, a binary operation on a set S is called associative if it satisfies the associative law. Z equals X for all X, Y, Z in S. Here, is used to replace the symbol of the operation, which may be any symbol, and even the absence of symbol as for multiplication. Z equals X Y Z for all X, Y, Z in S. The associative law can also be expressed in functional notation, thus, F, Z equals F. Generalized associative law. If a binary operation is associative, repeated application of the operation produces the same result regardless how valid pairs of parentheses are inserted in the expression. This is called the generalized associative law. For instance, a product of four elements may be written in 5 possible ways. C, D, D, add, A. If the product operation is associative, the generalized associative law says that all these formulas will yield the same result, making the parenthesis unnecessary. Thus, the product can be written unambiguously as A, B, C, D. Examples. Some examples of associative operations include the following. The concatenation of the 3 strings, hello, world, can be computed by concatenating the first 2 strings and appending the 3rd string, or by joining the 2nd and 3rd string and concatenating the 1st string with the result. The two methods produce the same result. String concatenation is associative. In arithmetic, addition and multiplication of real numbers are associative, i.e., because of associativity, the grouping parentheses can be omitted without ambiguity. Addition and multiplication of complex numbers and quaternions are associative. Addition of octonions is also associative, but multiplication of octonions is non-associative. The greatest common divisor and least common multiple functions act associatively, taking the intersection or the union of sets. If M is some set and S denotes the set of all functions from M to M, then the operation of functional composition on S is associative. Slightly more generally, given 4 sets M, N, P and Q, with H, M to N, N to P, and F, P to Q, then, as before. In short, composition of maps is always associative. Consider a set with 3 elements, A, B, and C. The following operation is associative. Thus, for example, A equals C equals A. This operation is not commutative, because matrices represent linear transformation functions, with matrix multiplication representing functional composition. One can immediately conclude that matrix multiplication is associative. Propositional logic. Rule of replacement in standard truth functional propositional logic. Association, or associativity, are 2 valid rules of replacement. The rules allow one to move parentheses in logical expressions in logical proofs. The rules are, and where is a metalogical symbol representing, can be replaced in a proof with truth functional connectives. Associativity is a property of some logical connectives of truth functional propositional logic. The following logical equivalences demonstrate that associativity is a property of particular connectives. The following are truth-functional tautologies: associativity of disjunction, associativity of conjunction, associativity of equivalence. Non-associativity. A binary operation on a set S that does not satisfy the associative law is called non-associative. Symbolically, for such an operation the order of evaluation does matter. For example, subtraction, division, exponentiation. Also note that infinite sums are not generally associative, for example, whereas the study of non-associative structures arises from reasons somewhat different from the mainstream of classical algebra. One area within non-associative algebra that has grown very large is that of Lie algebras. There the associative law is replaced by the Jacobi identity. Lie algebras abstract the essential nature of infinitesimal transformations, and have become ubiquitous in mathematics. There are other specific types of non-associative structures that have been studied in depth. These tend to come from some specific applications or areas such as combinatorial mathematics. Other examples are quasi-group, quasi-field, non-associative ring, non-associative algebra and commutative non-associative magmass. Non-associativity of floating-point calculation in mathematics. Addition and multiplication of real numbers is associative. By contrast, in computer science, the addition and multiplication of floating-point numbers is not associative, as rounding errors are introduced when dissimilar-sized values are joined together. To illustrate this, consider a floating-point representation with a 4-bit mantissa. Plus 1.0002 times 24 equals 1.0002 times 21 plus 1.0002 times 24 equals 1.0012 times 24 1.0002 times 20 plus equals 1.0002 times 20 plus 1.0002 times 24 equals 1.0002 times 24. Even though most computers compute with a 24 or 53 bits of mantissa, this is an important source of rounding error, and approaches such as the Cohen summation algorithm are ways to minimize the errors. It can be especially problematic in parallel computing. Notation for non-associative operations in general. Parentheses must be used to indicate the order of evaluation if a non-associative operation appears more than once in an expression. However, mathematicians agree on a particular order of evaluation for several common non-associative operations. This is simply a notational convention to avoid parentheses. A left associative operation is a non-associative operation that is conventionally evaluated from left to right, i.e., while a right associative operation is conventionally evaluated from right to left. Both left associative and right associative operations occur. Left associative operations include the following: subtraction and division of real numbers. Function application. This notation can be motivated by the currying isomorphism. Right associative operations include the following: exponentiation of real numbers. The reason exponentiation is right associative is that a repeated left associative exponentiation operation would be less useful. Multiple appearances could be rewritten with multiplication. Tetration via the up arrow operator. Function definition. Using right associative notation for these operations can be motivated by the Curry-Howard correspondence and by the currying isomorphism. Non-associative operations for which no conventional evaluation order is defined include the following: taking the cross product of 3 vectors, taking the pairwise average of real numbers. Taking the relative complement of sets is not the same as